Good morning. The last time I was in this building was actually during my doctorate, and you can tell from my gray whiskers that'll be a long time when Silicon Graphics was here. So we're going to have a little bit of history in this slide deck as well. So I'm going to talk about distributed SQL and why this is the backbone for modern SaaS, so software as a service applications. Okay, a bit of background about me. So I was at Pinterest, VP of Data Engineering at Pinterest for 5 years, semi-retired from there. Now doing a little bit of angel investing and also advising and consulting. I was also at Twilio for about 3 years. And so I've got a bit of experience with data systems. Okay, so some SaaS industry examples just to set the scene here. So there are the cloud SaaS providers, such as AWS, Azure, and GCP, Google Cloud Platform. There's also the platforms built on top of that, like Databricks, Twilio, TiDB Cloud, of course. And then the applications on top of that, such as Salesforce, Workday, and Slack. And of course, we also have internal SaaS systems as well, such as Pinterest. We'd have our internal SaaS platforms that we built on top of the cloud, and also on top of some of the data providers as well. So where has SaaS come, and where are we at with SaaS, and where is it going? So there's actually a massive amount of usage of SaaS today. We're growing at about 20% year over year, all the way from the revenue for the applications, and the top 5 have about 40% of the share, and it's about $178 billion last year. For platform as a service, the top 5 has 60% share, and that's about $120 billion per year. And then the infrastructure as a service, that's about $140 billion, and the top 5 have 80% share. So it's a continual growth. And what's really driving the growth now is generative AI and more ML and AI applications. And we have the generative AI biggest companies, such as OpenAI, there's GitHub Copilot, Midjourney for images, Perplexity for search and large language models, and also Claude as well. And then we have the applications that are starting to adopt more and more generative AI as well, and that's really driving a lot of additional revenue. Okay, so when we look at the business of software as a service, in order to figure out what the technical requirements are and what kind of data systems and applications and architecture you need need to go, first of all, to the KPIs, and then we'll go through the business requirements. Okay, so the KPIs, really, there are 4 major KPIs. One is in terms of acquiring customers. How many free trials can you get? How many customers can you get doing trials? And then what's the conversion rate for them to sign up to actually pay for a service? You then want to, of course, make some revenue. And you're trying to increase the revenue that you're making over an annual basis, and usually do this with a subscription model. And you're trying to increase the usage among your existing customers. And then you look at the net dollar retention. How much revenue are you retaining from existing customers? You try and reduce the churn of those customers and increase the amount they use by innovating and adding more functionality for those customers. And then you also look at the gross margin. So over time, you want to try and reduce your costs per revenue dollar, and you want to increase the percentage of revenue that you're making above your cost of goods sold. Okay, so let's translate those requirements into technical requirements. When you're expanding your customer base, you need a scalable architecture so that you can rapidly grow. You need to be able to support many customers in a multi-tenant environment. Some of those customers are going to be small, some of those customers will be large. And you want to increase the usage. And over time, so you've got to horizontally scale, but you also need to take into account the spikes in traffic that can occur. And those can be predictable, such as around Thanksgiving when people are purchasing a lot of products, or they can be unpredictable spikes. And so you need to have your architecture that can handle those things. You also want to have continuous innovation. So you have agile development and be able to iterate really quickly and be able to update your systems fast. You want to retain your current customers. And so for current customers, they always want to have high availability of 3 or 4 nines availability. And they also need to have security. They need to have some compliance. So there's additional regulatory things they need there. And you want to optimize your costs. So you want to reduce your costs per dollar that you're making over time and have this elastic capability to increase the amount of instances you have and reduce them when you don't need them anymore. Okay, so what's the reference architecture for a software as a service system? So here we have our users coming in, usually through a web browser. They go through an access layer. There's a control plane here that is saying what you can access, what you can't access. The application is using, which has some business logic here, is using several different stores. Starts off with a relational database and then adds other stores like NoSQL, search, real-time analytics. And of course, you're gathering all this data so you can then use it for machine learning. You can use it for analytics on your back end. And you're also monitoring and doing anomaly detection. And then from this learning, you can create some large language models so that you can help the users get their questions answered. And you can start to make your application more efficient. And of course, you integrate with some third-party providers as well, such as for billing, such as Square, Plaid, and maybe do some messaging and communication with Twilio and other ones too. Okay, so what are the challenges with this reference architecture? So there are really 4 substantially major challenges. There are other ones too, but these are really the big ones. The scalability, high availability, multi-tenancy, and also your architectural complexity, and you're trying to reduce that complexity. And so I'm going to talk through each one of these challenges so you understand a bit more in detail about these challenges. So most companies will start off with a relational database. So when they're a startup, it's the first thing they do. And so the bigger companies as well. So you start off with a SQL database and you're building out with your first customers. And your data volume starts to increase and you need to handle more and more transactions. And so in order to do that, you start sharding that database. Then over time, you want to have a bit more elasticity, less operational costs. So you want to automate the sharding. And so you start enabling resharding to be done. And then you find that your SQL database can't do everything that you want. You also want to, as well as do transactions, you want to do some search capabilities. You want to do some NoSQL, so have really high scale, really large tables. You want to do some real-time analytics. And we add in more and more of these systems. Okay? So when this starts to occur, then you've got a job to do to keep all your data in sync between these systems. You've got to manage all the schemas between these systems, and you're supporting hundreds to thousands of different schemas and tables. And so things start to get more and more complex. You're spending more and more time on your data systems. And this becomes a really big operational challenge. And you start creating a data engineering team and to take care of a lot of this. Okay, so then we go to high availability. And of course, you want to have a really highly available system that can deal with outages. Because if you ever work in a cloud environment, you know that instances can go down quite frequently, and even the availability zones can go down too. Hopefully not regions, but you need to also take that into account as you grow so your customers have confidence in your systems. So you start off with your traffic going to one database, or it could be one region here. And then you start doing replicas, and you have to decide, am I going to try and keep my data strongly consistent between the two systems, or am I going to have slight inconsistency here? So when the databases are in the same region and different availability zones, you can keep them strongly consistent because the latency is really low. But say you need to have a database in Asia and one here, or one in Europe, then the latency is too large to keep that consistent, and so then you have, this is more of a backup. So you trade off between consistency and latency, and then when the database goes down, which it happens to everyone at some point, then you change your traffic to go to the one that the backup or the secondary. Okay, and there's some operational cost around this, just making sure that this is going to work when it actually happens, and then having the ability to actually go and do this quickly. And then for some SaaS providers, they actually need to be on multi-cloud. So SaaS providers like Databricks, for example, they need to be in every cloud, and so you need to make sure that your database will actually work in those other environments as well, and rather than use different ones in different environments. Okay, then we go to multi-tenancy. So what's multi-tenancy? This is the ability to be able to separate your storage and compute for each one of your customers so that a customer can't see anyone else's data, and they're not affected by the performance of other customers in terms of their usage. Okay? And so the major challenges around multi-tenancy are data and workload isolation. How do you isolate the data from each customer? How do you isolate the workloads from each customer? Having elastic scalability so that as customers have increased in their growth, then you're able to scale with that. As they have spikes in their traffic, you can handle that. You also want to be able to have flexible capacity planning as well. And then, over time, you also want to reduce your costs so that having all these customers isn't going to cost a massive amount of money. And you want to reduce the operational complexity. Okay, so quite a few things here with multi-tenancy. And usually when you start off with the one database, and you put all your customers into this one database because they're small customers at the beginning. And then over time, you think, oh, maybe I should try and make it, I need to have some bigger customers, and maybe I should have an architecture where I have one database for each customer. And then you think, well, actually, for cost, the most optimal thing is to have a hybrid architecture here where I put all my small customers into one database and the bigger customers into their separate database. And so for each one of these, they actually can solve some of these architectural challenges. So this one here has the least cost and least operational complexity. This one here has workload isolation and flexible capacity planning. And this one here has cost efficiency. It also has workload isolation and flexible tenant capacity planning. But none of these solve all the challenges above. Okay, then you've got architectural complexity. When I showed the charts at the beginning there, we had multiple different data stores, and we wanted to keep them all in sync. And so you want to be able to rapidly innovate, and you're going to have frequent schema changes that you want to be able to have across all these systems, and you want to be able to upgrade your databases. All of these things are happening, and it's very hard to do when you've got so many data stores on the back end. And then you've got your data spread across these multiple systems, so you've got data consistency issues. Customers will see that the data in search is not up to date with the transactional data, and you want to have the data access controls and compliance, and also have the ability to go multi-cloud if you need to as a SaaS company. Okay, so from all of these challenges, you can see actually a lot of all these problems are down to the data storage systems. And you've got these 4 different storage systems, going from a relational database, a NoSQL database, so you can have scale and large tables, going to like a search, and also real-time analytics here. And you want to integrate this, of course, with your offline data systems for machine learning and for batch analytics. So you've got scalability limitations, high availability limitations, multi-tenant complexities, and architectural complexity. Okay, so a little bit of history here. So we started off back in the day with relational databases, and the latest ones at the moment that are open source are MySQL and Postgres. And the advantages of relational are it's transactional, so you can update money, you can update things in a transactional way. You have full SQL capabilities to do analytics and other things. The data has high integrity, so that means that when you have a relation between one table and the other table, the relation is there. And but you do have operational complexity when you're starting to scale and you need a shard, and it's not a multi-tenant environment. And then over time, NoSQL databases were created. So this is a schemaless design. So you have a flexible schema. You have much higher scalability. Tables can go larger. You're able to grow fast. They grow. You have higher reliability and failover here, but you don't have the data consistency necessarily. And you have limited SQL capabilities, so you can only query on rows or section of rows. Okay, so that's why you need both of these. Whereas distributed SQL actually has the scalability and reliability of traditional databases, scalability and reliability of NoSQL, but with the functionality of your relational database. And so examples of that are Google Cloud Spanner, TiDB, Cockroach, and Yugabyte. Okay, so what does a distributed SQL architecture look like? This is almost like an architecture picture. So you separate the compute layer from the storage layer. The compute layer, you enable to have the protocols of being able to use SQL for MySQL or Postgres. You're able to do schema management easily, optimize the SQL queries, and also you have an execution engine that works in parallel and is distributed SQL. And on the back, for storage, you transparently shard. There's automatic load balancing. There's automatic distributed transactions, and you take care of replication of the data to multiple different instances. And then when you get to like an advanced distributed SQL store, start adding these advanced capabilities like multi-tenancy, being able to do transactions and analytics in the same database. So being able to do analytics without affecting the transactional latencies. You can do point-in-time recovery, flashback to a previous point in time where the data was there and what the state was at that point. You're able to do serverless, so you can spin up machine, or you can just execute a transaction or spin up a database real easily. And you also have vector search capabilities where you can start adding in multimedia type columns for your large language models and AI. Okay, so I want to go through how a distributed SQL engine can solve the challenges that we talked about before. So for scalability, we've decoupled the storage with the compute. We have horizontal scalability, so nodes, as the traffic increases, nodes can be added into the pool to take care of the additional traffic, and so you're scaling out there. There's also some intelligence in the workload distribution, and so there's actually monitoring of how the cluster is performing, and when additional workloads are required, and the scheduling of those workloads are allocated to the right compute to where the data is, and the data is replicated a number of times. And so there's load balancing here across and prioritization of the different jobs so that transactional jobs don't get affected by analytical jobs, for example. And then there's distributed query processing, where you can query across multiple nodes to get the results back even faster. So this makes the scalability much easier. Then we have high availability. Apps are querying the instances below. We want to have strong consistency across the different nodes. And so there's replication of the data across these different nodes, so that if one node goes down, which happens all the time, or you want to replace a node, then you have automatic failover to the other ones that have the data, and that's transparent. And then you also have the flexibility of deploying into multiple regions, multiple availability zones, and if you want, can go to multiple clouds as well, so you have higher availability. Then in terms of multi-tenancy, your customers are usually different sizes of usage. There's usually an exponential curve where 80% of your revenue is made by 20% of your customers. And so these are the different customers, tenant 1, tenant 2, tenant 3. They need a different amount of compute. They use a different amount of storage. And you need a resource manager to dynamically allocate the resources for these different usages. And then, of course, the customers want to be billed for how much they use. And so you do billing. You basically need to measure how much the usage is, and you can do billing for each customer that's specific to them. You also have more simplified operations with distributed SQL. So you have a seamless schema evolution. So you still have a relational schema, but you're able to change that and update your database really easily. You're able to upgrade with zero downtime. I remember, well, at Pinterest, it would take us between half a year and a year to upgrade a MySQL across all of our fleet. It would take a half a year to a year to upgrade all of our HBase across all our fleet. And use a system like TiDB, it can take 1 to 2 days, including all the testing you do. So having zero downtime for upgrading is important. Being able to have controls of your access management and unifying that. And also minimizing your cost across all these different tenants. So distributed SQL can take care of this. And this really empowers teams to then focus on innovating on top of the data systems and do less administration. And I don't think anyone likes being woken up in the middle of the night to be able to go and fix a system. And so when systems can auto-fix themselves, it makes your life much happier, get better sleep. Okay, so what changes to the reference architecture that we had before, where we have the SQL, the NoSQL, the search, the real-time analytics? Well, all of that can be replaced with distributed SQL. And distributed SQL does a lot of self-management. And so it enables you to scale up your business. And if you started with distributed SQL in the first place, you would have a much easier life than going through the evolution that many companies have gone through before. And if you've gone through that evolution, then you want to consolidate the number of systems you've got, so you just have distributed SQL, and you don't have to manage so many systems, and it takes care of all the things that we talked about before. So why distributed SQL for software as a service? Well, always on reliability. You're able to accelerate your innovation more, so you're focusing on the business logic rather than having to keep all these databases in sync and doing all the management and maintenance of that, and all the integration required for that. You have multi-tenancy out of the box for yourself. You're able to grow to the sizes that Max was describing, if not higher over time. And then you're also optimizing your cost. You're minimizing the amount of cost for this infrastructure. And so the cost is much less having one system than having all these different data stores from before. So I want to go through 2 use cases at the moment, 2 real-life customers that have replaced their systems with distributed SQL. The first one is Catalyst, which is a leading customer success platform, and they had Postgres and Elasticsearch. They found that they had poor scalability. The analytics was complex. It was difficult to change the schemas, and the costs were high. And so they replaced those two systems with TiDB. So they had real-time integration, they had linear scalability, and they were able to evolve their schema much easier. And the results were, then they had a single system for all the data, they had 10x query performance, and enhanced the scalability and reduced the costs. Next one is Pinterest, which I know and love, and actually was part of this project. So we had 50 HBase clusters. HBase is hardly being used or hardly being contributed to in the open source world now. It's being used still a lot. And we had 50 HBase clusters, and it was like a ticking time bomb for us. We knew that at some point we were going to have major problems because there's always security patches you got to add, there's operating system changes you got to roll out. And we wanted to move to new instance types, and we knew that this was not going to be possible with HBase. And we had applied hundreds of patches to HBase. We had 9,000 EC2 instances and over 6 petabytes of data in these clusters. High total cost of ownership. We had 5 people full-time just looking after maintaining HBase. And there was data consistency issues, so the users would see that the data wasn't always consistent because there wasn't data consistency between tables. And we had scalability issues. We wanted to have more than 500 million items for shopping in our catalog, and we knew that HBase was going to break at some point. And we also had a lot of functionality issues. So we had to build functionality on top of HBase, including the ability to have secondary indexes, have a search capability, have a graph data capability, do analytics. There were lots of things that we built on top of HBase. And all these things had to be maintained as well. And we still had data consistency issues. We still had performance issues and scalability issues. So we replaced most of these systems with TiDB. The other ones we decided to put into a bespoke analytics and bespoke KV store. But everything else went to TiDB. And in the first 2 months of going to production, I think we only had 1 alert. Whereas with HBase, we were having alerts every single day. OK, so this improved our P99 latency between 2 and 10x. The cost of our infra went down between 50 and 80%, depending on the use case. Strong data consistency, and we had auto scaling. And then developers were freed up to do more things that they love, like software engineering, rather than the maintenance of the system. I'd like to thank Lychee for doing most of that work, so thank you, Lychee. OK. So preparing for the future. So the future of software as a service. So it's still got a lot of growth and a lot more adoption. There's more and more growth driven by AI and machine learning. As you can see, data management is the key to all of this, and being able to reduce the number of systems really will help you with that. So my recommendation, if you aren't using distributed SQL already, you should be. And you should definitely be using it instead of some of these services like MySQL, Aurora, HBase, and there's much more as well. So when you go about this, if you haven't started the journey yet, so you want to choose a more mature product for distributed SQL rather than one that's like a early stage startup so that there's more functionality there. You want to, when you start, leverage the cloud offerings so they have a managed service, so it's much easier just to get going. You want to identify a pain point that you have today with scaling or performance, or a new use case that you would like to try this for, and use that and make sure that then that works. And then scale up your adoption. Try and replace everything that you had before. So thank you very much for taking time to listen to this talk. I'd like to thank Lee Chen as well for helping with the slide deck. Thank you.